Okay, we continue on with the compressed air. This will be the third video, I believe. Second part of the ways to compress air. We discussed previously about elevated water of lakes and uh, ponds and streams, creeks and rivers, and even the elevated water from lunar elevation of tidal in places like Fundy Bay. Um, one of the next things that I want to cover, which is more popular today, is wind turbines. Now, um, there's going to be a lot of people who are not going to like what I'm going to tell you. Um, I have my own speculation as to why it's the way that it is, and I've never been one to not give my opinion, and I'm going to give you my opinion on these. The most popular wind turbines that are being built right now are called horizontal wind turbines. And they get their title based on the direction of the output shafts from the turbine blades. Uh, these big monsters, the three-bladed monsters, sometimes four-bladed monsters that you see that are erected, have what they call a horizontal uh, shaft that outputs off of the blades. Now, you know, these things are just stupid. I mean, seriously, people, they're just stupid. And now there's a bunch of you that are kicking and spitting and reaching to switch this thing off. And if you switch it off, then you'll never learn whether or not I have a good reason for it. And then when you find out later that I do, you'll be kicking yourself because you didn't listen to it. If you own stock in these things right now and you can get some other dummy to buy them, go ahead and do it. Save your butts. If you don't, your your horizontal wind turbines will be sold down and torn down and sold for scrap. So listen to what I'm about to tell you, why horizontal wind turbines are bad. First of all, you have to input the output from the wind blades into your generator. With a horizontal wind turbine, your generators have to be up high on the tower because your output shafts from your turbine blades are horizontal. And doesn't matter how long you make them, they're not going to reach the ground in any way, shape, or form that you can hang a generator on it. And so that means that you have to put these generators way up on top of these masts. Now, let's talk about the problems that that design has. First of all, you can't put a spindly mast up and put these heavy machines up there because these generators are the size of a good size F-150 Ford pickup truck, and they weigh much more. So you better make the mast that you're going to put this thing up on there very heavy because it not only has to hold the weight of the wind pressed against it that are pushing against the turbine blades, it also has to hold this heavy mass of generator. The other problem with this is that you put one of these towers up and you are going to have a minimum height that the tower has to be based on the length of the arms of your turbine itself. So you've got to go way up in the air with these things. Now, you can't hand this generator to a fella and say, go up on the top there and put this generator up. No, you have got to rent some very, very expensive weightlifting equipment, some cranes, to raise this stuff to the top of these towers. And these cranes are not cheap. They're very expensive. And these cranes are very expensive to insure, which is one of the reasons that they're so expensive to rent one to come down and put the generator up there. And if you ever have to make any repairs or replacement of that generator, you're going to have to rent these cranes again. Then, by the nature of the design of these things, the blades they put on these turbines, you know, I've heard the engineers in that bragging about how well they're balanced. I'm going to tell you what, those blades are heavy. You damn well better have them balanced. So now you have these huge monstrous vanes that, again, you're going to have to use these big cranes to pick up and mount on the output shafts, or I'm sorry, on the input shafts on the wind turbines on these horizontal shafts. So now you're adding even more weight onto this tower. So now between the weight of the blades, the torque placed on the tower due to the wind contacting the tower, plus the weight of your power generation equipment and the electrical systems you require to keep the system stable. Plus, in some cases, they have fire suppression systems installed in them because the things are notorious for catching on fire. Because they're so high up in the air, you can't have people standing there monitoring them for problems because problems don't occur that often. If you had 50 of them all in one room, that would be a different thing. But these things are so far set away from each other that, and they're so far up in the air that having anybody monitor them doesn't make much sense. So they put in automatic fire suppression control systems, which adds to the weight of it. Now there's another problem that occurs with this style of wind turbine. You cannot guy the towers. They have to be freestanding. If you put a guy wire up, then the guy wire is going to interfere with the rotating turbine blades. No matter what you do, you cannot guide these, which means the towers have to be bigger and beefier again. And uh, let's not say that these things don't blow over. I have seen videos of these things blowing over because even as massive as they made the towers, they failed in a windstorm. It was catastrophic when it was done. This multi-million dollar device was a smoking pile of trash in the middle of the field. The horizontal wind turbines are just the wrong way to do it. Now, introduce a new style, not a new style, but let's say a less common style than what has appeared, and that would be a vertical wind turbine. Now, way back in the old days, the horizontal were the traditional. And I'm not sure at what point that somebody came up with the idea of the vertical wind turbines. I haven't researched it, and maybe someday when I'm old and crotchety and I don't have anything else to do, I'll go online and research it. But vertical wind turbines use a vertical drive shaft, and they have a basically the shaft goes up vertically in the tower, and the vanes that catch the wind are mounted on that shaft going up and down, and they're convex and concave. So you would have the vanes for catching the wind are not flat. They're convex and concave. Convex on the outside, concave on the inside. And you mount one to the vertical shaft here, and then the next one is mounted on the other side facing in the other direction. So when the wind is blowing, it hits the round area and the wind slips around it easily. But on this area, it's concave, so it catches the wind and it causes them to rotate the shaft that they're sitting on. And then the one that was facing originally with the convex side facing the wind rotates around until its concave side comes facing the wind, and then it rotates around. And then while one is the concave is facing the wind, the other one is slipstreaming until it rotates around 180 degrees, and their position of capturing wind or slipstreaming the wind changes places. Now, the ones that I have seen built by a man in Lancaster, New York, um, he had built one of these. I think he had 6 of these wind capture devices on his vertical shaft, and the thing was very good at collecting wind energy. Now, um, it would take it might take 4 of these. Of course, it depends on how big you build the thing. Also, I could build one of these so large that that it would make a presentation to the wind equal to what these big 3-bladed wind turbines do. That's not logical, though. The bigger you build something, the more energy is going to be wasted in running it. So, while big is beautiful, you're going to want to find that fine line where the cost begins to transgress the logic of the build versus your losses. So, as I'm talking here, the one that I'm going to be speaking of is going to have a base, and I would consider this to be a large one. Is going to have a base of 20 feet, and the other issue with this now, one of the things that you have to understand with wind, when you step outside in your front yard and you feel wind blowing against your face, um, that is not going to be equal to the same wind that is blowing 20 feet above your head, or, excuse me, or 50 feet above your head, or even 100 feet above your head. At all those different levels, on a given day, the wind speeds are different. So you're not going to, it's not going to be easy to find which one would be the best to place these, and so some homework needs to be done. And the problem with doing the homework with anything in regards to weather is that it changes, from day to day, from month to month, from year to year, from century to century. It's just not something that you can nail down, to be consistent. And the biggest problem is the day-to-day basis. If you can have wind speeds changing at elevation several times during a single day. So how do you make a presentation with these things that that will get you the most out of the footprint on the ground that you have of your wind turbine? Well, the solution to that is that you take these 20-foot diameter and 20-foot high uh, uh, vertical blade assemblies that I was telling you about with the convex concave uh, vanes on the thing, and you stack them, and you stack them as high as you want to. Your only limitations are going to be the frames that you put these things in, because the frame on the very bottom is going to have to be robust enough to support whatever maximum number of wind turbines that you put on it. Now, this is an advantage to the horizontal turbines because you can only put up one horizontal turbine. With the vertical wind turbines, you can stack them, and you can stack them as high as your design allows you to stack them. Because you don't have this far-reaching arms of the vertical wind turbines that you have with the horizontal, which means that you can also guide them. Now, when you start putting up guy wires on vertical structures, the guy wires add a tremendous amount of stability. And because the guy wires have such a high ability to not interfere with wind because they're steel and they're round and they're smooth. They're not going to cut the wind very much. So you can, you can throw up a set of guy wires on every single pod that you put up, and every set of guy wires is going to add more stability to your vertical build. So you can get a pretty high wind ripping through those things, and the guy wires are going to hold them down so that they don't get blown over. Now, let's get back to the blades for a second in these things. The horizontal wind turbines, the blades are made out of a very dense composite. I believe it's a plexiglass based. With I watched a video of them building these, and I don't remember. I know that they had to use something nylon screening or something like that to make them strong enough. But these blades become very, very heavy. I was watching a video of them moving one blade down the street with a tractor trailer, and the blades are huge. It was not a small tractor; it was a heavy tractor, and they were very. I think the thing had 16 axles on the trailer for moving this thing down the road, or 8 axles, I think it was. But anyway, they were very heavy. Now, if you really want to screw up a sailboat, and what moves a sailboat? Wind. You really want to screw up a sailboat, take down those cloth sails and replace them with fiberglass. Yeah, it doesn't work. There's a reason that they don't use fiberglass to make the sails in a sailboat. So what we're going to be doing is we're basically going to be going back to the old-fashioned sail like they used to use on the ships. We're going to change it slightly because we're going to put up sails that could be left up on the mast for 10 years. So we're going to make those cloth sails rigid so that they don't so that they maintain their convex concave shape. Now we can do that with sparring with ribs, or we can densen up the sail material itself. From a weight point of view, the sparring in the ribs is more intelligent, and that's probably exactly what we would do, would be to spar rib these things to maintain their convex concave shape. My friend in Lancaster, or I'm sorry, not Lancaster, but Lackawanna, New York, I believe that he was using a thin plastic composite, and that probably makes the most sense, because being the thin plastic, it's rigid, and the plastics, you can put chemicals on them that prevent sun damage to them. And you, with a single spar in the center of them, you can keep them from collapsing from reversed wind pressure on the surface. Now I've been playing around with this design, and I have other designs that will eliminate the drag resistance against the back of these vanes for catching the wind, but I don't want to get too complex with this, so I'm going to stick pretty much right now with this basic design just for simplicity. So now you say, okay, in this particular area where I'm installing it, there's a fair number of trees and there's houses around, buildings around, and whatnot. So it probably doesn't make much sense to install one of these things anywhere near under 30 feet. Now you might be on a mountaintop where all of the trees have been cut down, and there's a pretty stiff breeze that runs across the top of that mountain. You may want to put one of these assemblies right flat on the ground because you get plenty of air across the top of that all the time. So it depends on your location on the design. So I'm going to talk about a design that requires your first one to be at a 30-foot level, so that that'll help you understand a little bit better on the transition of the energy from the blades to your ground port. Um, uh, Now the towers. I've got to make my timer visible here. I'm already 20 minutes into this thing. The towers um, would be guide down into position. The vertical shaft would go down to the ground, and now, because I'm talking about compressed air with this series, not generating electricity, we're going to go to the ground with air compressors. And one of the problems with the wind turbines is that they have a very narrow window of wind speed with the horizontal turbines that they're using now. They have to be up to a certain speed before the generators can start gathering electricity and generating it, send it out, and that they reach their maximum speed relatively quickly, where if the wind gets too fast, you could damage the generators. So what they actually do is they begin tipping the vanes of the horizontal wind turbines into the wind to cut down on how much torque is input into the generator, which is a waste because if you start deflecting the wind that you were trying to collect, now you're no longer collecting it, you're deflecting it. So you're losing an opportunity to collect with that. With the compressors, they immediately begin compressing air on the first rotation of the shaft, and they continue to compress more and more air the faster they're turned. So we're not going to encourage this thing not to collect the air. We're going to tell it to always collect as much possible energy as it can to the air as it's flowing through. The only thing that we're going to have to worry about then is how much torque our shafts that are being used to transfer that energy down to the compressors, which means if we only have one set of turbines up there, the shafts don't have to be really strong. But when you start increasing the numbers of the turbines that you put up on top there, the shafts are going to have to be bigger and heavier going down to the ground. So what that means is when you first start building these, before you put your shaft into it, you're going to say, how high might we possibly be going with this? And the shaft that you're going to put into it at the bottom is going to be rather robust. If we wanted to say between 1 and 5, we can use a small shaft. Between 5 and 6, we have to use a medium-sized shaft. And between 6 and 10, we have to use a heavy shaft. So on the first layer of them, you use the heavy shaft. On the second layer of them, you use a medium-sized shaft. On the third layer of them, you use the lighter shaft. And that reduces the weight of your system builds uh, to run for maximum build. So so we put up this tower now that's going to be 30 feet in the air. And at the first platform that we're going to be setting our first set of wind turbine blades on, that shaft is mounted into a bearing at that floor where that shaft comes up through it. And the shaft is going to be set up with a dovetail design where there is a tongue and groove. So the shaft that comes up out of this floor on the first plate is going to come up out of the floor, and it's going to have a shaft in it like this. So if you rotate the shaft, you won't see the slot. But when you rotate it this way, you see the slot. Now, what that is an engage point for an additional shaft. So now you have this shaft coming up out of the floor on your first level. Then the next shaft that goes up to the next level has a tongue in it that fits down inside this shaft so that when they rotate together. Now that shaft then goes straight down to the ground, and when it reaches the ground, it then attaches to an air compressor or to a series of air compressors. Um, if you want, by a series of it, if any of you have ever seen any of the videos of the old planes that actually had the pistons right behind the propeller, and there was like 12 of them that were situated around the shaft of the airplane engine. You could put your compressors around your drive shaft that comes down out of your wind turbine like that, so that in lower wind speeds you might only engage one of these air compressors, and at the higher wind speeds you engage all 12 of them, and that would be computer controlled based on the torque coming out of the shaft. So now on the ground, back to what we were talking about in the previous video, you're just collecting compressed air. So on that first level, now you install one of those shafts with the convex concave uh, wind vanes attached to a shaft to it, and um, and then you put another plate on top of it, which would be the top for this one and the bottom for the next one that goes onto it, and then you guy wire those plates to the ground. The first plate is guy wired to the ground. And then after you put your first level of wind turbine into it, you guide the second plate to the ground, and that whole system is very secure in the wind. Um, and so you build a second unit and you put it on top of that, and you repeat that process again. You put the extension shaft in, you build the the turbine blades around it, you cap it and guy it, and now we have two wind vanes that are now attached to this vertical shaft, which means that at some point we may have the wind actually a little bit faster into one than it is the other, and so the energy that the one is gathering is going to be wasted because it's going to be rotating the other one up to its speed, and in doing that is going to add to its load. So what you want to be able to do is you want to be able to disengage the ones that are not inputting into the shaft because of the difference in wind speeds. So what you do with that is you attach these uh, blade assemblies to the vertical shaft with what's called a clutched bearing. A clutched bearing, when you turn it in one direction, it disengages and it just rotates freely. When you turn it in the other direction, it engages on the shaft and locks into it and turns it. This prevents the slower turning wind turbines from putting drag on the shaft. So um, the different levels, if the wind speeds are equal, will all collectively input into the shaft. But if you get a radical difference of wind speed in another area, the ones that can't contribute to the input automatically drop out. And this is very good design because it conserves energy and not driving a non-functioning turbine blade and turning it into a propeller or a fan instead of a device for gathering um, wind. Okay. Now, again, as I said before, you can stack these things. If you happen to be in an area where there's never very much lower wind speed, then you could build a tower as high as one of these horizontal wind turbines, and then start stacking your collection blades up that high to where the wind speed is. and the cost of building these is going to be a lot less expensive than these monsters that they're talking people into investing into. Uh, the other thing is that the maintenance on them is going to be a lot less expensive. You can rig these things so that on the top, instead of mounting the last set of blades, you put a small jib crane up on the top, and now you can use that jib crane for bringing up repair materials or whatever up to do repairs on this vertical tower, or it could even be built so that you put on the next level that you're going to put up for the wind vanes themselves, and then move your jib crane up to the top of that after it's guyed, of course, and then your jib crane follows up to the top of these towers and stays in place once the tower is built, so that your mechanicals can be serviced. And I don't know if OSHA still allows it or not. I know that they have done it in construction in the past, but you can actually use these jib cranes to bring up elevators for people to ride on. So um, you might have this thing set up to with a basket on it that you could climb into with your tool belt, and then run the jib crane from that basket and hoist yourself up to the top so that you can work on this thing. So you might have two arms on this jib crane, one for moving you up and down, and the other for moving materials and up and down for maintenance and build and whatnot. Much less expensive for the cost of one day's rental of one of the cranes that they use to put up these horizontal monsters. You could build one of these systems on the top of your vertical wind turbines, and forever have access to that building for materials and manpower and whatnot. Um, and they don't have to be extremely heavy, because the things that you're lifting are all very light. All of your turbine blades are uh, sail weight. We're not even pulling up anything anywhere near as heavy as the generators on those things, much less the blades for the install. So it just makes a lot of sense cost-wise to build and insurance-wise to cover, because if it doesn't blow over easy, you're not going to have to spend much insurance for them when they blow over. And the materials for building the things are much, much less expensive than a horizontal. Now, the opinion that I was going to keep to myself, um, I'm totally convinced that the big mouths in the wind industry were owned by the fossil fuel people. They did not want these inexpensive wind turbines being built, because that would only encourage you to build more. They needed to make a system that would keep the average investor out of these things, and it worked like a charm. Your average person, when they were looking for investors on these things, they were looking for $500,000 investors. With a vertical wind turbine, we would be able to take investments from everyone in a community of $20 once a year for 10 years to pay for these things. And in the result of building this, their electric bills go down by 9/10. So your local community could certainly afford to pay for these things for you, because they're going to have a lot of extra money left over every month. Um, so, um, for those of you that were trapped in that, and made investments in these horizontal wind turbines, um, sometimes you're the windshield and sometimes you're the bug. Okay, it's getting too long right now. I'll switch off from here, and my next is going to be, I think I'll do solar panels next. Okay, take care.